All right, guys, this is our last limit topic, believe it or not. We started distance learning doing limits, and we are about wrapping them up. We just finished talking about absolute value limits, and now we're going to talk about limits to infinity. I just want to highlight, when I talk about limits to infinity, I don't necessarily mean that the answer is infinity or negative infinity. I mean as x approaches infinity or negative infinity. That's what I mean by limits to infinity. Not necessarily that the answer has to be that. It could be. The answer could be infinity or negative infinity, but that's not technically what an infinite limit is. Okay, we're talking about as x approaches infinity or negative infinity, okay? All right, so when we talk about limits to infinity, we're going to break them down into three different categories because each category is going to have a different way to solve it. So the first category I want to look at are top-heavy functions. So if you remember top-heavy functions from our rational function days, they were ones where there were more blank in the numerator than the denominator. That was degrees, right? When we had more degrees in the numerator and the denominator. So if you look at something like part A down below here, we'll get to that in a minute, but you can see it's 7x to the 12th plus 2x to the 4th plus 3. That means there are 12 degrees in the denominator. There are only 2 degrees in the 12 degrees in the numerator, 2 degrees in the denominator. That would be a top-heavy function. But we'll get to that one in a minute. But before we get to that, I want to think about this function f of x, which is equal to x squared plus 1, and I want to know what happens to x, okay, or what happens to the term as x gets bigger. So let's say when x is 0, if I plug in 0 into x squared plus 1, my answer would just be 1. It would be 0 squared, right, plus 1. So in that scenario, 100% of my answer, or the value, 100% comes from that plus 1, right? The x squared term gave me nothing. It gave me 0. So 100% of my answer came from that 1 at the end, okay? But when I plug in 1, I get 1 squared plus 1. I get an answer of 2. Now in this case, only 50% of my answer came from the plus 1. Right, one of those two came from the x squared term, and 1 came from the plus 1 at the end. So notice that 1 didn't have quite as big of an impact. It still had a big impact, but not as much as when x was 0. When x is 2, I plug in 2, I get 2 squared plus 1, I get 5. In that case, that plus 1 at the end only accounts for 20% of your answer. Only 20% comes from that plus 1, right? 4 came from the x squared term, because a 2 squared is 4. The plus 1 only accounted for 1, so 1 out of 5 is just 20%. When I plug in 4 for x, I get 4 squared plus 1, I get 17. In that case, I'll do the math for you. That's roughly 6% comes from the plus 1. 1 out of the 17, that's about 6%. So only 6% came from the plus 1. And believe it or not, it gets even worse. When I plug in 8, I get 8 squared is 64 plus 1. That's an answer of 65. That plus 1 at the end, okay, only accounts for 2%. Okay. So notice here, what happens to that plus 1 in terms of its impact on my overall answer? And I kind of spelled it out for us, and I said, notice as x gets bigger, the x squared term begins to dominate. And you can imagine as x gets bigger and bigger and bigger, that x squared term is just going to absolutely dominate the final answer. That plus 1 really isn't going to have that big of an impact, right? Yeah, it adds 1 to it, but if we get numbers in the billions and you add 1 to it, is it really going to make that big of a difference? If you have $5 billion and then someone gives you $1 more, is that going to make much of a difference to you? Probably not. No. So that's an important concept, that as we go towards infinity, as x gets infinitely bigger, or conversely, negative infinity gets infinitely smaller, that plus 1, that constant at the end, whether it's 1 or 10 or 50 or 100, eventually it's not going to matter, because that squared term, or whatever that term that's being raised to a power is going to dominate. All right, so let's just keep that principle in mind as we start taking a look at problem A. All right, so this says the limit as x approaches infinity of that function. Okay, and the question I'm asking you is, before we even get to the limit, and I'm writing up here, is x gets infinitely big, will all pieces of the equation matter the same? Well, we just saw a minute ago that as we get infinitely big, the constants really do not have an impact. So guys, when I'm evaluating the limit, you can ignore the 3 and the 1. They're not going to have an impact. As we just saw above, it's going to get smaller and smaller and smaller. This is only when it's infinite limits, right? We're only talking about infinite limits. But as we deal with infinite limits, those constants will not matter. And guys, guess what? When we think about this numerator, as x gets infinitely big, which one of these two terms is going to dominate? Is the x to the 12th eventually going to take over, or is x to the 4th? Well, it's the x to the 12th term that's going to begin to dominate. It's going to dwarf that 2x to the 4th, so much so that once we get to really, really big numbers in the billions and the trillions and the quadrillions, I don't even know what numbers come after that, this term is not going to matter either. And that same principle applies to that in the denominator. So believe it or not, as x gets infinitely big, when we evaluate the limits, the only terms we need to worry about when it's top-heavy are the leading terms, right? Terms with the highest degree, both in the numerator and the denominator. So let's take a look at what we have left over. So really, when we're evaluating the limits, we're really only looking at 7x to the 12th over 50x squared. Those are the terms that are really going to matter. Well, if those are the terms that are really going to matter, is there any way I can combine and simplify this? I could really simplify this to 7 over 50, those numbers. X to the 12th over x squared would simplify to x to the 10th. So when I'm evaluating the limits, this is really the function that I should be looking at. It's going to have the same limit as my original one would. All right? So the way we would actually solve this limit is to actually go back and think about the end behavior. So if I think about the end behavior of the graph of 7 over 50 x to the 10th, that's going to have the same end behavior as my original function. And since it's a positive LC, and it's an even exponent, right? I know my end behavior is going to go like this. And think about this. That arrow to the left really represents as x goes towards negative infinity. This arrow to the right really represents what the graph does as it goes towards positive infinity. So what would this limit be as x goes towards positive infinity? I would just be looking at my end behavior, looking at this arrow here. That arrow's pointed up. So my answer would just be positive infinity. These are the hardest limits, the top-heavy limits. The other two limit scenarios are much easier. So be a little bit patient. This takes a little bit of time. But the nice thing about this, it's repeatable. Okay, it's repeatable. So let's go to the next one. The limit as x approaches negative infinity of the same function. Well, we know the end behavior of the function. We understand the rationale behind that. We know that the end behavior is this. And as I wrote above, the right arrow represents x going towards positive infinity. The left arrow represents what x does as it goes towards negative infinity. So what is the graph doing as x goes towards negative infinity? It is going up. This arrow is pointed up. Hence, my answer is still negative infinity. Right? If the end behavior is up in both directions, then the answer should be infinity. All right, so let's take a look at a few more. The limit as x approaches infinity of x. You may say, Mr. Bodner, how do I know if that's top heavy or bottom heavy? X is really just x over 1. That's really a top heavy function. So again, what I would do is evaluate the end behavior of the function x, since there's nothing to simplify. And that would be that end behavior because it's positive LC and an odd exponent. You might need to go back and review your end behavior rules. So as x goes towards positive infinity, that's the right arrow, and that right arrow is pointed up. So my answer here would just be positive infinity. I would encourage you at this point, if you're feeling pretty confident, try D&E, pause the video, try D&E, and then unpause it and see if you get the same answers I do. If you still don't feel very comfortable, you can follow along with me. All right, so the limit as x approaches negative infinity of negative 2x plus 3. That is a top-heavy function because I can really think about this again as being over 1. The end behavior, since it's in negative LC and an odd exponent, the end behavior is going to look like that. And it says as x goes towards negative infinity, so that is the arrow on the left. What's this arrow on the left doing? It's pointed up. So my answer would be positive infinity. And then the last one, E, is that big long expression there. The nice thing is I'm only worried about the terms with the highest exponent in each, the numerator and the denominator, so that doesn't matter, that doesn't matter, that doesn't matter, that doesn't matter, that doesn't matter. I'm only worried about negative 11x to the 7th over 4x cubed, which can be simplified to negative 11 over 4 x to the 4th. That's an even exponent and a negative leading coefficient. So both arrows are pointed down towards negative infinity. So my answer would just be negative infinity. Okay, so notice in this case for every answer we either had negative infinity or positive infinity. Okay, so that's a nice little trick to remember this. Or if you get stuck, it's always a 50-50 guess. Your answer is always infinity or negative infinity when top heavy. Okay, when top heavy, it's always infinity or negative infinity. All right, so that's the hardest one. You got to the hardest one. Let's now go to some more straightforward ones. Bottom heavy functions. Remember, what is a bottom heavy function? A bottom heavy function are ones where there are more degrees in the denominator than the numerator. All right, so I want you to think back to rational functions and what it meant in terms of the horizontal asymptote when it was bottom heavy. What was the horizontal asymptote in every case? And if you can remember, I'll be very impressed. What was that horizontal asymptote? It was always 0. It was always the line y equals 0. And what that meant graphically was it really didn't matter what the graph was or where the vertical asymptotes were. I'm just going to draw in a sample graph, but it really could be anything. Right? It really could be anything. Let's say we had a couple asymptotes here, I don't know, at 2 and negative 1. It doesn't matter. Eventually, no matter what the graph did, it always had to go towards 0 as you went out towards the right. And again, it doesn't really matter what it does in between. I don't know, maybe it went something like that and then did something like that. But eventually, both sides of the graph as we went out infinitely to the right and infinitely to the left always went to 0. The graph always went to 0. So what do you think what that means? I can't speak. What do you think that means in terms of the limit? Well, that just means the limit as you go towards infinity or negative infinity is always just 0. It's really just saying, what does the graph do as you go out in this direction? The graph goes towards 0. So this is really easy, bottom heavy ones. The answer is just always 0. The tricky part is just making sure that it is a bottom heavy function. So the answer when it's bottom heavy, answer is always 0 when bottom heavy. Okay? So when we had infinite limits that were top heavy, it was infinity or negative infinity. When it's bottom heavy, it's always 0. So those ones are my favorite because you don't even have to think about it. Once you determine it's bottom heavy, answer is always 0. And it's for that reason, because it creates a horizontal asymptote. That means that's where the graph's going to go. All right, last one, guys. You guys are doing great. Balanced functions. Okay, if you remember what a balanced function was, it was ones where they're their same degrees in the numerator and denominator. Okay, so same degrees. And this one's going to be fairly straightforward too. So what happens in this case? Well, let's just jump right into a limit and see what happens. So we've already talked about this concept, right? That as x goes towards infinity or negative infinity, the constants don't matter, right? As the numbers get infinitely big, subtracting 1 or adding even a number like 1,000 isn't going to matter. okay? Because the number is just going to get infinitely big. So that really leaves me with 6x to the fifth in this example over 12x to the fifth. All right, what happens to those x to the fifths? They're really just going to cancel each other out, right? Whatever, if I plug in 3 to the fifth in the numerator, I have to plug 3 to the fifth in the denominator. Those are always just going to cancel out. So since those guys always cancel each other out, what are you left with? You're really just left with 6 over 12, which in this case simplifies to 1 over 2. Guess what? That's your limit. Okay, that's your limit. So in a balanced function where everything just cancels each other out, your limit is always the ratio of your leading coefficient over your leading coefficient in the denominator, right? So leading coefficient in the numerator over leading coefficient in the denominator. Just a reminder, leading coefficient is the term with the highest degree. It may not always come first. So I could get tricky and put the leading coefficient at the end. So just watch out. Term with the highest exponent. So watch out for that. Okay, watch out. In problem A, there was only one term that had an exponent in them, so you didn't have to worry about that. All right, so summarizing, summary of rules of limits approaching infinity. When it's top-heavy, our answers are either infinity or negative infinity. Life's great, only 2 answers. Our life gets even better when it's bottom-heavy because the answer is always, always, always 0. And when it's balanced, okay, your answer is just the ratio of your leading coefficient, LC, over leading coefficient, LC, okay? So those are our rules for infinity. I've got 10 practice problems here for you to do. I'm looking at them. Again, just sit there, take the time to analyze whether it's top-heavy, bottom-heavy, or balanced. And then based off your analysis there, just apply the rules that we've learned. Top-heavy will be the hardest. We might need to talk about it in class next time, which is fine. We'll talk about it then. But do your best, forget the rest, and do these 10 for homework, and then I will see you guys next class.